Right, so this section is on the range equation. We're going to take a look at how this affects us and what we use it for. We utilize a technique called the pulse wave in order to make ultrasound images. And a pulse wave is sent out, and reflections arrive from structures along the path of the wave. And when those reflections, echoes come back to our transducer, we're able to detect them and uh, put out a reasonable, uh, analyze the strength of them, and then plot it on our screen at the location where the object was from our transducer. And we utilize the um, sound, the time that the sound is traveling in order to determine the depth of our reflectors. So the pulse echo technique is simply pulses of sound are sent into the tissues. Echoes returning from the tissue provide anatomic information, and those echoes that return tell us information about the tissue characteristics. Is the tissue anechoic, echoic, brightly echoic, those sort of things. That is the information we're getting back from the echoes. Elapsed time in ultrasound is how we calculate the distance from the face of the transducer to the target. And then, of course, that same amount of time is what it takes for the reflected sound to return to the probe, to the crystals. This is just an example of a reflection of a pulse coming down, reflecting off of a specular reflector and heading directly back to the transducer. It is traveling through a liquid that is anechoic, so you're not seeing other echoes come off of it. It's just going all the way down to our reflector and coming back. And because each pulse takes the same amount of time to come down and go back, we know exactly how deep that reflector is. So time of flight, or go return time, is how we measure reflector depth. Time and depth are interchangeable in many aspects of sonography. In fact, when we talk about a particular type of control, we have words for it such as the time gain compensation, or synonymously the depth gain compensation. The point is that depth and time are synonyms when we're talking about ultrasound. So time of flight is related directly to the depth of the reflector. Shallow reflections return echoes quickly, and deep reflectors return echoes much later. We do know that sound has an average speed in soft tissue of 1540 meters per second, though all the tissues of the body travel either faster or slower than that. A reflector that is twice as deep as another will have a time of flight twice as long as the shallower reflector. And this is the equation that you may have seen notes earlier. Um, the depth of our reflector is 1.54 millimeters per microsecond times the time of flight in microseconds divided by 2. So if you do the math, that works out to 13 microseconds per centimeter. So we have this idea, um, sound, or yeah, sound travels in 1 centimeter. Sound will travel sound travels 1 centimeter in 6.5 microseconds. Sound travels to a reflector and back, which is 1 centimeter deep, in twice that, or 13 microseconds. So this becomes our 13 microsecond uh, kind of rule, if you will. So for every 13 microseconds, we're getting information back from reflectors which are 1 centimeter deeper. So if the depth of your reflector is 1 centimeter, it takes 13 microseconds to travel there and back. So the total distance traveled is 2 centimeters. And we just double that for 2 centimeters reflector, increase it for a 3 centimeter, 4 centimeter, and 10 centimeter. The pulse repetition period is how long it takes to reach our maximum imaging depth. So we set the maximum imaging depth by determining what our pulse repetition period we want to be. Now, when we turn the knob on the machine, it doesn't say pulse repetition period, it says depth. So we should know that we are adjusting our imaging depth based on this pulse repetition period. So the reciprocal of the pulse repetition period is the pulse repetition frequency. And so therefore we should know that the deeper we image, the lower the PRF, pulse repetition frequency, is going to be. So sound energy is pulsed in the body at rates that vary with imaging depth. Okay? We call that rate the PRF, or the pulse repetition frequency. The pulse repetition period is the time between one pulse to the other. The pulse repetition frequency is the number of those pulses that occur in 1 second. So imaging depth and PRF are reciprocals because PRF and PRP are reciprocals. When depth is shallow, PRF is high. When depth is deep, PRF is low. So we also have this equation that Edelman gives us of the PRF is 77,000 centimeters per second divided by the imaging depth. Just PRF is inversely proportional to imaging depth. I can tell you for myself, I have never used this equation of PRF is 77,000 centimeters per second divided by the imaging depth. I have never used that equation for anything. Edelman will use it to calculate the frame rates when we get to that. But I'm going to show you a different way to do it. And like I say, I've never had to use this. Okay, PRF is reciprocal of PRP, PRP reciprocal of PRF. And as it says here, if imaging depth is 1 centimeter, the PRP will be 13 microseconds. And if that's the case, then the PRF will be the reciprocal of 13 microseconds, or 1 over 13 microseconds. And that will conclude our discussion of the time of flight. So